Hi, welcome to me313, Mechanical Engineering Thermodynamics. The topic of this lecture is Rankine regeneration, and the section in the textbook is 10.6. So here are the four learning outcomes. At the end of this, you'll understand why regeneration using feed water heaters increases the cycle efficiency for Rankine cycles. You'll know the difference between an open and a closed feed water heater. You'll be able to apply energy balances to open and closed feed water heaters, and at the end you'll be able to solve for the thermal efficiency of a Rankine cycle with an open feed water heater. All right, so first I want to talk a little bit about why feed water heaters are more efficient, how they increase the efficiency, and so it helps to understand that in terms of entropy generation going on in the Rankine cycle. So what I have drawn on this diagram in green here is the simple Rankine cycle where we have 4 points. This would be the outlet from the condenser, traditionally point 4, inlet to the condenser at point 1, and then the boiler is points 2 to 3. Right. Now, thinking in terms of what's actually going on when we're going from 2 to 3, this is water, compressed liquid water, that's in a boiler, being added to the boiler, and then that boiler is essentially bringing it up eventually to this temperature up here, which is T3. So what that means is that my boiler has to be operating at least T3. In fact, it's probably something a little bit larger than T3. So when the water that's first exiting the pump here at point 2, it's being heated by something at T3. It's way down here at T2, and so there's a lot of heat. There's a large temperature differential going between T2 and T3 as the water first exits. And so we could think of T2 as T low and think of T3 as T high. And if we go back to kind of concepts we knew in Chapter 7, where the entropy generation is going to be, well, the amount of heat that's going into the temperature sink minus the heat that's coming out from the temperature source. And since T low is less than T high, that value is not only going to be greater than 0, the larger the difference between T low and T high, the greater that is, the larger this value is. And we know if we're generating entropy, that what we're doing effectively is destroying exergy. And so exergy destroyed is going to be the temperature times Ps, where this is the temperature of the environment, usually some T naught value. And so we're destroying a whole lot of exergy as we go from this point just a little bit up to the side, and we destroy a little bit less exergy, but we're destroying a lot of exergy here when we've got this large temperature difference. So one way we can get around that is to use what's called a feed water heater, where what effectively we're going to do is we're going to take some of the material halfway through the turbine, and then we're going to bleed it off, and then go ahead and add it through a heat exchanger, and we're going to use that to heat up the water at the low temperature. And that way we're going to go ahead and increase the efficiency, and we increase it by generating less entropy. Okay? So this is the way a feed water heater looks. And so there's two different types, open and closed. So first we'll discuss what an open feed water heater looks like. And so here's our Rankine system with a feed water heater. I've got my boiler here on the left. Here's my turbine, a single turbine, and the condenser. And what I have now is this box, which is called an open feed water heater. And you can think of it as just a large tank with 3 openings in it, 2 that go in that way for an inlet and 1 that comes out. It's nothing more than a large tank. And so what I'm doing is halfway through the turbine at intermediate pressure, I bleed off a fraction of the mass flow rate. I'll call that fraction Y, some number between 0 and 1. It's a fraction of it, and I add it in here. So this is going to be at some medium temperature. We call it Tm. We're up here at T high, and then this is going to be one of the T low. At some medium pressure, now after we've gone through the condenser and gone through the pump, this is also going to be more or less at T low, depending on what the outlet from the turbine was. But it's more or less T low, and I'm going to be mixing T medium with T low to come out with some new temperature here, call it Tm prime. It's going to be maybe something between Tm and Tl. But what I've done is I've brought Tl up to Tm prime, brought it up to some intermediate pressure, or intermediate temperature in the feed water heater. And so then my boiler is only going to be adding temperatures in the middle. Okay. Now, one of the things that happens with a feed water heater, there's another piece of equipment that comes in, is that I've now got 2 pumps instead of 1. But here I'm going from P low to some P middle, and this is going from P middle up to P high. So what I've done is I've replaced one large pump with two smaller pumps. There's going to be a little bit of a cost to that, but not a substantial. I'm not doubling the number of pumps or doubling a number of identical pumps. I've replaced one large with two smaller. There's a little bit of extra infrastructure, but not too much. As I mentioned, an open feed water heater is really just a big, large tank. So there's actually not a lot of components that go into it. So now what's going to be different, we're going to modify this Rankine cycle that I have over here on the left. I've got some new states here. In fact, you see we have a total of 7 states, and we have 3 pressures. And so I think it's really helpful with these is to sketch up isobars that we have. And so that right there would be my P high isobar. Over here would be my P low. And let's put one in the middle right there. And so now if we look at our points, okay, here's point 1 going into the boiler. Point 5 is, I'm sorry, this is point 4 on that diagram. It's point 4 going into the boiler. Point 5 is coming out of the boiler. And then we drop down at that intermediate pressure. There is point 6, and that right over there is point 7. And so point 6, and I've kind of shown it exactly in the saturated curve. It might be a little superheated, but it's going to be something around there. And then what's happening is I've gone through the condenser. So after I go through the condenser at 7, I'm going to come over to, I'm sorry, that's not point 4. That is point 1, which is the outlet of the condenser. That's point 1. And then point 2 goes up right there, so it's a little bit above it. And now point 2 is being mixed with point 6 to generate point 3 at that intermediate pressure. So point 3 would be right there. And now I go from point 3 up to the high, which would be point 4. And so there is the input to the boiler. Let me erase some of that. I'm sorry, I kind of mislabeled that early on. Okay, there we go. So here's point 4. That's the input to the boiler right there. Point 1 is the outlet from the condenser, and we've got these extra points here, 6, 3, and 2, that are in intermediate pressure. So we're going to solve a problem here in the middle in a minute here, and you're going to see where all those exactly come off. But before we do that, let me talk about what is a closed feed water heater, because there's 2 different kinds that you can have. And so what I show in the diagram over here is a closed feed water heater, and this right here is the closed feed water heater. And what it means is that instead of just being a big, large tank, it's a heat exchanger. Usually it's kind of a countercurrent heat exchanger. You can kind of see here where it's showing this line here is separate, and the fluid's going to move through. This is going to be the cold fluid getting warmed up. This is the hot fluid cooling down a little bit, but they don't mix. And there's a reason why you might use a closed feed water heater. If you look at what's going on, is that this pump down here is going from P low all the way up to P high, because these lines are separate. So these pressures can be different. So the pressure in that line right over here is the high pressure. This right over here is P middle, and this over here is P high. Okay? So now I have one small pump, I have one large pump, but there's only a fraction of material going through it. If we pull off Y there, we have 1 minus Y fraction going through here. So we've got a small amount of material going through this large pump and a small amount of material going through this smaller pump right over here. Sorry, this is the larger pump. This is the smaller pump. And then over here, this is more or less like an open feed water heater or just a mixing tank. Again, it's just a big, large tank where the two get mixed together. And so after I've brought it up to the high pressure, I can then mix them together, and it goes into my boiler here. So let's draw that up here again. Let's see if I don't make a mistake this time on my points. So I'm going to, again, I think it helps to draw up some isobars, and so you can have your intermediate pressure to know where those points all are going to appear. All right. So I'm going to start off at point 1, and let's correctly label point 1 there, assuming that the condenser outlet is a saturated liquid. And we can go ahead and label some of the other things we know. The input to the turbine right over here is going to be 0.6. Halfway through, it's down here at 0.7, and then here's the outlet. That is at 0.8. Right. So now let's go ahead and look at what's going on. We'll start off at point 1 again. We have point 1 goes through a pump all the way up to the high pressure. So point 1 goes all the way to the high pressure. So point 2 is on that high pressure line right there. Right. And now we have 7, and 7, which is a superheated vapor or maybe a saturated vapor, is getting cooled off, so it's going to be moving somewhere over here on the left, so it might be somewhere right around there. I'm drawing it kind of as a saturated liquid, but somewhere pretty close to that point right there. And then we can look at 2, right? So here's my point 2 coming through here. It's getting warmed up, so point 9 is going to be something warmer than that. So it's going to be also at that same pressure. So there's going to end up being point 9 that moves through, and I have point 3. And so then if we go ahead and look at point 3, it's now getting pumped with my pump. It's going to now move up to the high pressure line. That would be point 4. So there's point 4 and point 9. And 4 and 9 are mixing. And since 4 and 9 are mixing, they're going to have to be, point 5 is going to have to be somewhere in the middle. Right? Clearly if I mix something hot and cold, I'm going to get something in the middle. So that right there is point 5. So I kind of a jumble of points down here, but it's good to recognize 2, 9, 5, and 4 at the high pressure. 3 and 7, right over here, are the only 2 that are at the intermediate pressure. And then 1 and 8 are down here at the lowest pressure. Now there's a couple other things we have to do before we can solve problems. We have all these extra states, which means we're going to have some extra energy balances. And so let's go through what the energy balances would look like. And we'll start off with the open feed water heater. So here's the open feed water heater. I have an inlet there, and an inlet there, and an outlet there. I'm sticking with the numbering that was on the previous diagram. And so let's just go ahead and apply a steady state energy balance to this, which says that the energy that goes in is the energy that goes out. We look at our energy coming in. I have this fraction y of the mass flow rate, so the m dot times y, and its enthalpy, which is H6, going in. Down here, I've got m dot, and the fraction is 1 minus y times H2, and that's going to be equal to m dot times H3. And those m dots all cancel, so you can just write y, H6 plus 1 minus y, H2 is going to be equal to H3. So there's my energy balance, and this is an independent equation if I know what fraction of material I am pulling off of the system. Let's look at the energy balance for an open feed water heater, because now what we have is we have 2 inlets and 2 outlets. That's kind of straightforward to do. So again, let's just look at the energy that goes in and balance that with the energy that goes out. And so what I have is, and I'm going to drop the mass flow rates here because I know they're going to cancel. I'm going to have y times H7 going in plus 1 minus y times H2 going out. I'm sorry, going in as well. And that's going to be equal to what goes out, which is going to end up being the fraction y H3 plus 1 minus y H9. So there's my energy balance for an open feed water heater. Okay, so let's wrap this up. Let's go ahead and solve a problem. We'll do just an open feed water heater here, and I'll leave the closed feed water heater for in class and in the homeworks. So here's my problem. I'll just put some numbers on it here. Outlet of the boiler, I'm at 15 megapascals and 600 degrees C. My intermediate pressure I've got at 1.2 megapascals. I got a fraction y, and my condenser is operating at 10 kilopascals. Right? And then we're going to make some other specifications on here. We're going to assume that this feed water heater, that we've got just the correct fraction, that 3 right over here is going to end up being equal to a saturated liquid, x equals 0. And so this is just going to be something specified in the problem. Often systems are designed such that that more or less works out. So I'm going to go ahead and specify that. And we'll also assume that our pumps are isentropic and our turbine is isentropic at this point, just to kind of simplify things and focus on the use of the feed water heater. Okay, I'm going to go ahead and solve this in EES. I think it's a little bit easier with Rankine cycles, so I have to look up all those values. So let me move over to EES. And so over here on the left, we go ahead and see my specifications. So at the top, I'm just specifying what was given in the problem, which was I'm at 15 megapascals and 600 degrees. That was at 0.5. My condenser is at 10 kPa, which is 0.7, and then we're operating that intermediate pressure at 1200 kPa. So I've got my unit system specification at the top. And then we have our constant pressure lines. So you can go back to that diagram we did a couple slides ago and see that 1 is equal to 7, that's the condenser. We have 4 and 5, so that's over there at the high pressure. and then 2 and 3, we're going up there at the middle pressure as 3 and 6. And then the last thing, X1, that's the outlet from the condenser, that is equal to 0. And I said we're going to make the assumption that X3 is equal to 0. That's the outlet from the feed water heater. So we'll just look at that for now. Okay, so here's my solution table. All my pressures are specified there. I've got my intermediate pressures, 2, 3, and 6. My high pressures, 4 and 5. There's the temperature. So a couple things are missing. Remember, once I have 2 intensive variables, I'm completely done. I need another thing at point 2, another one at 4, and then 6 and 7. Okay. Now 5, 6, and 7 is going through the turbine. If that's isentropic, I'm going to find the entropy at 5 and make that 6 and 7. That would be an isentropic step. 1 to 2 is the low pressure pump. 3 to 4 is the high pressure pump. And if I make both of those isentropic, I can specify those entropies. So that's how I'm going to get those last 4 intensive variables. Okay, so let me go ahead and modify my text here for that. Okay, so here's the new specifications that I have. If I do that, let's go ahead and just look at what I have written. My constant entropy. First, I specified entropy at 1, 3, and 5 using X and P pairs for the first 2, and then P and T at the boiler. And then I have 4 statements, which is the isentropic. 1 to 2 and 3 to 4, which is the pump, the low and high pressure pump. 5 to 6 and 6 to 7 is the turbine. And I've written them here on the same line, separated with a semicolon. That was just in terms of saving some space. Those can all be on their own line. So now if we look at our solution table here, we realize we've got entropy at every step and pressure at every stage. 2 intensive variables that are independent. So our problem's completely specified, but completely solved now, essentially. Now we just calculate enthalpy values and look at some of our energy balances. So that's going to be the last step that I have. So let me go ahead and remove this this last set of comments. Right, and we first go ahead and focus on what I have written, and then we'll look at the solution. So since I have S and P everywhere, I have my duplicate statement, finding the enthalpy at S and P. Again, I'm using duplicate just in terms of efficiency, because I have 7 to find. And then I've got my first law relations. The heat input to the boiler, that's the difference between 5 and 4. I'm doing everything on a per mass basis here. The heat output in the condenser, that's 7 to 1. Now note, only 1 minus Y is going through the condenser, so I have to weight that by 1 minus Y, which is actually good. Helps my efficiency because I'm losing less heat out. And then here's my feed water heater energy balance. Y and H6, 1 minus Y, H2 is equal to H3, what we wrote before. And then the network of the cycles, the difference between Q in and Q out. My efficiency is the network over Q in. Now note what this extra equation did is actually going to go ahead and give me this feed water heater is going to go ahead and tell me what Y is. This is going to tell me the fraction of steam that I need to pull off. So let's go ahead and look at our solution here. Okay, my efficiency is 46%. The fraction that I'm pulling off is 22.73%. So that's the amount that was required such that H3, the outlet from the open feed water heater, is exactly a saturated liquid. And then I've got my Q in and Q out values, which aren't necessarily quite as important once I know what my efficiency is at 46%, which is an improvement. A couple of more things we can do that's kind of interesting was, as I said, I specified that the outlet from the open feed water heater was a compressed or saturated liquid. That was this X3 is equal to 0. What would be interesting is to find out how does the efficiency change as I change that value X3. Maybe I don't condense it all the way to a liquid. Maybe I bring it down to a quality of like 0.1 or 0.2. So we can do that in EES. Let's look at another function. What I'm going to do is I'll look at create a table. So I'm going to do that by I'm going to comment out X3, which means I'm not specifying it. And then I'm going to go under tables, and I'm going to create what's called a parametric table. And what I want to do is I want to find out what the effect of X3 is. So that's going to be my variable in the table. and then I want to find out how that affects the efficiency. So effectively, I'm creating a table of X3 and efficiency values. I can more or less solve the same EES problem again and again and again with different values of X3 and the efficiency. Okay? So here's the parametric table that I have. I'm going to enter values of X3, and I'm going to solve this problem again and again for what the efficiency is. And if I hit this little triangle up here, I can specify that the first value is, I'll say it's 0, and we'll look at quality values from 0 to 0.3. So I'm just going to have EES go ahead and generate the values in my table for me. And I'm going to hit this little green arrow to solve it. And really what it does is just solves EES 10 times with different values of X3. And what you can see here is as the outlet from the feed water heater is actually a little bit of a mixture, not all the way saturated liquid, my efficiency actually increases a little bit. In fact, we can plot that if we want to look at it. So let's create a plot window. This will be an XY plot. I'm just going to have X as a function, or X as a function of the efficiency here. So now I've got the efficiency as a function of the outlet quality from 0 to 0.3. We see actually the efficiency increases. So what that seems to indicate is that we actually would want the outlet from feed water heater not to be a saturated liquid, but maybe somewhat superheated. And that's not necessarily true. And so let me explain why that's not necessarily the way that we want to do it. I'm going to come back to our solution here. Let's just go back to the problem that we solved where we specified that it was a compressed liquid, saturated liquid, X equals 0. And let's look at let's go ahead and not do this on a per mass basis. Let's make it extensive by specifying that, for example, let's say that this is a 100 megawatt power plant. So work is the total work extensive, and it's calculate what the mass flow rate is that would be required moving through the system. So M times W net, from the W net was in a per mass basis. So if I go ahead and solve that, my mass flow rate is 78. So what that means is I need 78 kilograms per second moving through the cycle if I've got my X3 at 0. Now what happens, remember that number 78. Let's go ahead and change this to 0.1. Okay, and solve that. Now mass went to 82. So it increased 4. Now it's 82, or about 5% increase in what the mass flow rate is moving through the system. But I haven't changed the net work that the system is producing. It's still producing 100 megawatts. So I've got the exact same functioning power plant, giving me the same energy, but now I've got a larger mass flow rate going through. And let's go back and look at our diagram. It might help us think about this. That's mass flow rate. That's what's coming in right here. All that mass is going through this pump right here. And it went from 78 to 82. For a system that was all generating the exact same 100 megawatts. So what it meant me as an engineer designing the power plant was I had to design in a bigger pump. Now you increase the efficiency, but by also increasing the mass flow rate, you didn't actually increase the amount of net work the system generated. It's still a 100 megawatt power plant. But I had to spec out a larger pump, which means the capital cost would have been larger. So you know, if I go ahead and keep moving this from 0 to 0.1 to 0.2, 0.3, although the thermal efficiency increases, I'm not necessarily making a better plant. I mean, you could just be building this incredibly expensive Taj Mahal power plant that has this incredibly high efficiency, but it's still a 100 megawatt power plant, the same thing that you could have that wasn't the Taj Mahal. So, there's some trade-offs there, so sometimes we don't want to focus too much on thermal efficiency and realize things such as capital costs. Now, costing is a little bit outside the purview of this class, and it's help you look in other courses, but it's a good thing to recognize why that is.